Vectors are, they're a way to represent certain quantities, other than just quantities that are a number, because like for example, velocity is not just a number, it's actually a number, but it has direction. And so that's what one thing vectors can be used for, and some others but too, but it's quantity that has magnitude and direction. So it's, mathematically speaking, what we say, it's a directed line segment. So here's an example of a vector. So instead of saying, well, you can go from here to here, either way, this is going to be our initial point, and then we got a terminal point. And so that's really the big change, I guess, you could say there. You got an initial point, and you got a terminal point. Names-wise, another thing to get used to between books and writing, writing things. The name of a vector in a book, they may just do a bold name. So this is vector AB. And so in the book, it just may be bolded, and you can tell, when something's bolded in a book. Now, you and I writing, bolding is not so easy. We have to sit there and color in. We don't want to do that, and so, yeah, we're going to use the vector designation here. Either, a lot of times I'll just do something like that. It could be just an arrow, but it's an arrow type looking thing. All right, and so yeah, this gives us, it's a vector AB, so it starts at A, goes to B, but we very well could name a vector by just a single letter designation. And so we could say, well, vector AB, well, let's just call that vector A, lowercase a. So anyway, the good thing, I guess we'll call it a good thing, is the position of the vector doesn't matter. And so if I have another vector, C to D, that's the exact same length, and it has the exact same angle, if you will, those two have the same magnitude and direction, if you will. Those two are equal. Those are equivalent. They're equal. If it has the same magnitude, same direction, those two are equal. So it doesn't matter the position of the vector as far as equality goes. Same magnitude, same length, and direction. All right. To add vectors, you put the initial point of 1, so if I've got vector A here, and then vector B is here, I want to add those two. You just put the terminal point of one to the initial point of the other, right? So we take A and then put the initial point of B to the terminal point of A. So that vector from that initial to that terminal, that's your addition of those two vectors. There's the tail there. All right. If we multiply, so if C is a scalar, which basically what that just means is just a number. So if C is just a scalar, we'll talk about multiplying vectors next time, but if C is a scalar, if I multiply that C times vector A, that just multiplies that vector by that scalar amount. So if you've got, here's A, well, 2A would just take that vector and multiply it, give it twice the length there. Half A would just take that vector and cut it in half. Same direction, just cuts it in half. So that's good news. And then if we take the scalar is negative, that's just gonna, what that does is, well, in this case the scalar is -1, so the 1 doesn't change it, but the negative, what that does is just flips it around, right? And so this is A, then negative A would just go and turn it the opposite direction. So, which then leads us then to, well, what about subtraction? So yeah, A minus B, if I use those same two there, well, A minus B, that would be A, if you thought about it, one way to think about it is, that's just adding a negative B to it. So if I take A and add to that minus B, so put, this would be, if that's B, then this is minus B. Right? Minus B is that. So add those two together, A and then minus B. Like that, it's a little length to it. So that vector right there would be A minus B. However, what we'll note there is that if I just did A and then put the initial point of B with that, then what I'll wind up with here, that's just B. So I put the two initial points together. Well, that's exactly A minus B is, put those two together, the two tails together, or the two terminal points together. Yeah, you get the same vector. It's the same vector because it's the same magnitude and length. Same magnitude and direction. That's the same, so that's the way to do it. Okay. Well, so that's fine, but what we're interested in is how do we represent vectors? How can we write these down and work with them? So yeah, let's do the two-dimensional rendition, and then that, of course, moves on. We can move on to the three-dimensional analogy of it. All right, so here's, we put it, vector A in 2 dimensions. If we put the initial point of A at 0, 0, talking about 2 dimensions. All right, so the terminal point then would be this point out here. Let's call it A1, A2. A1, A2 would be the terminal point. The initial point, 0, 0. Terminal point is A1, A2. Well, the way we represent vectors, or one way we represent vectors, is then by using these what you call them? Grouping symbols, pointed grouping symbols, what we would call them. I don't know what they're really referred to, but that's the way we refer to vectors in 2 dimensions anyway. Yeah, you just use the terminal point, or what would be the terminal point if the initial point was 0, 0. Okay. Now, to move that vector around, what we can think of it is, well, this just, A1 just gives me the horizontal displacement. And then A2 is going to give me the vertical displacement. Because, yeah, we don't have to necessarily lock our vector in to be initial point 0, 0. This would be the same vector out here. Same magnitude, same direction, same angle. So that's still vector A. So what does A1 and A2 refer to? Well, it's not, I can't go with, in this case, if it's here, this is A1, this is A2, but what I'm saying is this is A1, and then this would be A2. Okay. So it's a vertical and horizontal displacement, or horizontal vertical displacement. So that allows us to move that thing around there. All right, well, like I said, the good news is a lot of times these three-dimensional, to extend this to three-dimensional, you just add that extra component. So yeah, in 3 dimensions, you're just going to add that third component there. So that'll give you the x displacement, the y displacement, if you will, and then the z displacement. So, good news on that. Now, it is important to note, though, that, all right, so if I say draw A equals 5, 3. Well, A equals 5, 3. One version of it, I guess we could put it anywhere you want, but A equals 5, 3 would be initial point 0, 0, so I would go out in the x direction 5, the y direction 3. And it's a vector. And so you have to be aware, if it just said, well, what about 7, 1? Well, that's not a vector, that's just a point. Okay, so the vector is the ones that have the grouping symbols like that. So this is just a point. So anyway. All right. So if I'm given A is x1, y1, and B is x2, y2, then what about AB vector, AB vectors? Because those 2 points, I mean, it doesn't say one is the origin. So what am I going to do there? I can't just put the vector symbols around one of those because that doesn't tell the story there for that AB vector. So I've got x1, y1 point, and then x2, y2. It's just, so I want that vector right there. Well, it turns out I can use kind of this A vector, but all I have to do is, let's just think about, well, what's this horizontal displacement? What's this vertical displacement? Well, this amount, this displacement here, what would it be? Just be the difference of your x's, right? And then that vertical displacement would be the difference of the y's. And so we can represent that AB vector by using this A vector because, it's just a vertical and horizontal displacement. Horizontal and vertical displacement. Make sense? So we can make a vector out of 2 points. So I think this is the phrase I'm going to use. Find vector A. That starts at the origin and is equivalent to AB vector, where A is for 4, -2, and B is 6, -3. So again, you just take, to get that vector, you just take the difference of the x's and then the difference of the y's. So that would be 2, -1. So that would be the equivalent vector there. Sometimes we'll need to talk about, of course, the magnitude of a vector. Or the length of a vector. Well, the good news is, well, if we just look at it, all right, so we've got this vector A, which, here we can X, A1, A2. So we can represent those. Well, if you just look at it from the geometric sense here, for 2 dimensions anyway, 3 dimensions follows suit. A1 is just this distance here, A2 would be this distance. So I'm talking about the length of that vector, so what would that length of that side be? Well, it's just the square root of Pythagorean theorem, right? The square root of these two, the sum of the squares. And of course, the notation for magnitude is your looks like your absolute values, but we're talking about a vector, so that the context there just means the magnitude of a vector. But like you said, it's just from Pythagorean theorem, right? The square root of A1 squared plus A2 squared. And again, if A is a 3-dimensional vector, magnitude of A is nicely, then the sum of the squares, square rooted still. So, yeah. For now anyway, the three-dimensional counterparts are very nice. They just add that extra component into it. All right.